Baik ya, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat siang semuanya, good afternoon. Oke, saya buka dulu ya. Oke, good afternoon everyone ya. Uh, Welcome to today's session ya of the UGC ya, Undip Global Classroom Program for the course Vector Calculus or Calculus 4 in uh, Mathematics Undip curriculum at the Department of Mathematics, Faculty of Science and Mathematics, Diponegoro University. Let me introduce my name. My name is Jovian Dian Pratama. Yeah, you can call me Jovian. I am a lecturer of vector calculus and coordinator of this course. Yeah. It is a great pleasure and honor for us to welcome our international guest lecturer from Universiti Teknologi Malaysia, ya, Dr. Mohd Ali Khameini Ahmad.
Yeah, yeah.
Sir. Okay.
Thank you.
Okay, before
Okay.
we begin our lecture, yes, please allow me to briefly introduce our guest speaker, ya. Oke. Oke, Dr. Mohd Ali Khameini Ahmad is currently a lecturer at Department of Mathematical Science, Faculty of Science, Universiti Teknologi Malaysia, and his research interest, is p-adic analysis, dynamical system, number theory, nonlinear analysis, and mathematical models in statistical mechanics, and he obtained doctoral philosophy, PhD in mathematics in international, Islamic University Malaysia or IIUM, in collaboration with University Paris S France, Okay, and so many publication, Dr. Ali has actively contribute in international research publication and become a presenter in conference and have a research grant, in mathematics, particularly in dynamical system and p-adic mathematical analysis, Okay. He also has an extensive teaching experience, in course such as calculus, nih, calculus, engineering mathematics, mathematical analysis, set theory and logic, engineering mathematics, and theory of matrix, Okay, today Dr. Ali will deliver a lecture on us, surface integral, and next week he will deliver our lecture in Green's theorem, for the second section. Okay, please join me in warmly welcoming Dr. Mohd Ali Khameini Ahmad. Okay, the time is yours, Dr. Ali.
Okay. Thank you very much for your introduction there. Good pleasure to be here. Can you hear my voice clearly?
Yes, clear, clear.
Yeah. Okay. Okay. So great to have all of you here. So I'm honored to be invited here as a guest lecturer. Okay. So, as mentioned by Dr. Jovian, right? Dr. Jovian, I will be lecturing on surface integral. Okay. So, is it okay if I start now?
Okay. Yes, yes.
Yes. Okay.
So
All right.
you can
So,
start now.
let me just share my screen. Okay. So, I'm accepting this because I'm going to teach also a similar topic here. So, allow me to use this writing. So I hope you can get some benefit from what I'm going to share with you today. So can all of you see my screen here?
Yes, Dr. Ali. You can see the whiteboard, right?
Okay. So if you can see, so let me just immediately so yeah, maybe let have some summary. So what I'm going to share with you today. So about the topic of this surface integral. Okay. All right. Okay. All right. So all of you have you learned this before? Surface integral?
Not yet,
So you
Mister, because wall of
the-
students not uh,
is a student who take this course?
it's not a particular course, but is our one of
I
our
did.
chapter. Yeah.
Okay, only general lecture only. Okay, something like that. Okay. So let me just share you. So let me make it as a proper lecture here. So on surface integral, if okay for all of you. So today I'm going to talk on surface integral here. Okay. So let's make it as a classical, okay? Classical lecture. So I'm writing here and then you will see what I'm going to explain to you. All right. So the topic on surface integral here, I will divide into three parts. So I will talk on what we call here the surface itself, the first part, and the second part, I will talk on the surface integral, okay? The surface integral of scalar, okay? Scalar field. And then the last part is about surface integral of vector field. Okay. All right. So this will be the main part of this guest lecture. So now let me move to the first topic here about surface. Okay. When we talk about surface integral, surely we need to know what is the main thing here, which is the surface here, right? So the surface here. So let me write it here, some summary diagram. So I have a surface. Okay. You can have some surface in space here. Okay. Baik. And then now what we are going to do in this particular interest here, which is space integral, we want to integrate, okay? We want to integrate over some surface there. Let me denote by surface here, okay? So you have a f ds, okay? So this is what we are going to do the whole lecture today, okay? So we are going to integrate the function here over some surface here. Since you have surface is two-dimensional, that's why more or less you have double sign of integral here. Wait, next, when this is function is we call a scalar because scalar it is just a number there. Okay, you can understand as a scalar here, like a number here. Whereas we can also integrate a vector field. Okay, vector field. So we denote by this is a vector field. and then over this surface. Okay, sigma, there's some surface here. Right. So this the two things that I'm going to share with you today. Okay, to discuss with you today. Baik. Yeah. So this is the surface integral of scalar field. So this is this second part here, and then this is the third part here. Surface integral of a vector. Okay. And then we have a special name for this. We call it as the vector, which is a flux. Okay, this is, you can call it as flux integral. Flux integral. Okay, so where you will integrate this vector field here. So more or less, you are computing how much the vector field across this surface. You understand that, you know. So you know, you see that vector field in the space, you can understand like this, some arrow here. So this is the F. So when you're computing this integral, we call it a flux. So we are measuring how much this vector field F is crossing this surface sigma. Wait. All right. So far, so good. Is my voice clear? So sometimes when I'm teaching here, my voice a little bit toned down. Can you hear me clearly?
Yes, sir. Very clear.
Yeah. Yeah. Okay. Thank you. All right. Yeah. Oh, yeah, now I can see. Okay. So now let me talk on the surface because the main agenda is surface here, right? So what is surface? Okay, surface you can understand as a two-dimensional object. Okay, two-dimensional object. Surface. Okay, understand that two-dimensional object here. So this is just briefly speaking. Okay, this is just two-dimensional object where you have two parameters to represent this object here. So that's another way you can understand what is two-dimensional object here. So before we talk further on surfaces, so there are two kinds of surface that we have. First is orientable, another is non-orientable. So what does it mean by orientable here? So you have some orientation for the surface there. Okay? You have, for example, just let me show you using example, a plane here. A plane is an orientable surface because you can have orientation for it. So how to orient? To make orientation for surface, make sigma 1 here. You can understand it using a normal, okay, unit normal. Okay, every surface you can orient it as unit normal. So you can have the normal here. Let me make it 1 going up here. Okay, so this is one direction here going up, right? Another way is going down there and 2 here. Okay? So you have two kinds of unit normal or direction that you can tell about the surface here, either going up or going down. So we call the surface sigma 1 as orientable surfaces. What else? Every surface that you can make it going up here or going down there. So then we have this as orientable surface. But another is like this is we call open surface. Okay, open surface because you have a boundary there. So if you are here, for example, if you walk there, so you want to change your orientation, your direction. So first your head is going up here, right? But if you want to go down there, So you change the direction, right? So when you change the direction, you are crossing some boundary there. So we call this as an open surface. So this open surface because you have some boundary there, and then you can go to another direction of the surface going down there. Similar here. Or you have a cone there. You have not a solid cone, only open cone there. Inside here is hollow there, right? So this is, and then you can, yeah, a cone cap. I mean, a cone cap here, you can wear it, this one. Okay. So this one you have, this is your orientation going outward. I said going outward, or you can have inside here, going inward, that orientation. Okay. And one, right. So this is another example of open surface. So what is the boundary here? So when you go here, if you are here, right, your head is going outward, right? And then you will go, and then this somehow like a circular shape will be your boundary, okay? Because this is where you change the direction of your head there, going inward, okay? So this is just open surface, and then this is example of orientable. And then is there any closed surface that orientable? Surely has. Yes. For example, sphere, okay? Sphere, okay? Yeah, sphere here, okay? So here you have also unit normal going outward here, or you can have unit normal going inward there. So you have always two direction. Okay, the surface you have two direction. Right, clear this one. Okay, so far so good. Just give you some meaning of surfaces here. Hopefully you can follow this one. Okay. So this is example of what we call closed surface. Okay, closed surface. Closed surface. Why I call it closed? You can understand it because there is no boundary here. Okay, there is no boundary here, right? And then even if you're outside here, you cannot go inside, more or less. Okay, more or less, you cannot go inside there. Right. So this is about orientable surface. Is there any non-orientable surface? So the second part here. The answer should be yes lah kan? Because I put it here. So you have orientable surface. So what is the orientable surface? You can understand you cannot orient it in this manner. You don't have these two direction of unit normal, the direction of the surface. Okay. Okay. The most classical example is the Mobius strip lah. Okay, the Mobius strip. You have paper there. Okay. And then if you glue it this way, and then you get the Mobius strip there. Okay. So let me just try to draw it. Hopefully it will be nice. Okay, you will have something like this one. Okay. You will have a twist there, more or less. Okay. Right. So this is one example of Mobius strip. Why I say so? Because if you are here, let me make it, you are here. Let me make it this way. If you are here, then you can travel across the surface without crossing the boundary. Okay. Like here, you need to cross the boundary, right? Meaning that you have only one direction there, more or less. So that's why we call it as a non-orientable surface. Example here, if you go to the back there, and then you go in front here, right? And then you will twist there, and then you go to the back here. And then you go at the back there, and then you come back here, and then you come in front here, twist, and then you come back here again. Right? So you more or less you can understand you as a normal there, direction of the surface. Enough for you, one direction, you can go all the way to all the surface there, Mobius strip. Okay? So this is one example of non-orientable Mobius strip. So this is you can understand as open, right? Open surface of non-orientable. Is there closed surface of non-orientable? Also, yes. We call it the Klein bottle. Klein bottle there. Okay, Klein bottle. So what you need to do, once you glue it here, you glue it this direction. So this one, the strip you have here, so you can make it this way. So first you glue it this direction, and then you glue it another way. Twist it. And then this one is not imaginable in the our three dimension, but there are many objects there. They make it this way. So if you want to try to draw it, first what you do is you glue this one, right, to make a cylinder there. So you glue this part with this one. So you get this cylinder where you have this direction at the top here, and the bottom here should be, let me make it in front. You have this direction, and then you have this direction here. And then you need to glue this one with this one, okay? So how to glue it? Yeah, there is no easy way. So you need to across 4 dimension it more or less. So you have these things, is this direction, right? So somehow you are only care about the topology. So you can somehow bend this one. You should bend it. You can bend it this way, right? You try to you are permit to do this, and then you will have something like this. Now you have this direction. Okay, because if you bend this one, you make it as this direction here. And then what you do, you try to glue it here, here. Then what you get will be something like this. You will cross this one. Somehow you have 4 dimensions there, and then you go there. You go there. Okay, this we call as a client bottle. This also non-orientable because you can go outside the bottle and you can go inside the bottle also. So only one direction you have. Okay, so you have this one, and then you will go there inside, and then you go inside, and you come up again. So this example of non-orientable surfaces. So just to share with you, this non-orientable because most of the time here we are not care about this non-orientable part, no? So we care only about these orientable surfaces. Okay. Baik. So that's a little bit on surface that we are going to deal with. Okay. So we have always orientable surfaces. Okay. So next part. So how to represent? How to represent this orientable surface? There are 3 ways I can class to represent this surface. The first way is to use parametric equation. Parametric equation. Okay. And the second one, you can represent using implicit function. Function implicitly. Implicit, let me make it implicit here. And then the third part is explicit. Okay. And then the most frequently appear here, more or less, I will deal with explicit form here. Baik. Okay, so far? Okay, good. Understand? You are still following? Okay.
Yes, Mister.
All right. Yeah. Okay. Baik. So now let me just explain one by one about this representation of surface. So how you can represent a surface using parametric equation. So if you know a line can be represented using one variable, right? Because line just one-dimensional object here. You represent it using time t, variable t. So for example, at time t, you have here t equal to t0, t equal to t1, for example. Okay. So you're using a vector there, right? So you have Let me make it xt I plus yt j plus zt k here. Okay. Baik. So you have this thing. Yeah, this you have three because in the three dimensional. So you have three direction here. I, j, and k there. Or you can write it in the vector form xt, yt, zt there. Okay. Baik. Similarly, you can represent surface using this parametric equation. But now instead of only one variable, you need two variables. As I mentioned before, you can understand surface as two parameter equation there. So let me write it here as follow. So I have R, so let me make it UV there. V equal to X a function of UV, I plus Y a function of UV, J plus Z function of UV. Okay. And now you need three coordinate lah, three direction because the surface usually lies on the three dimensional. And then the UV here, this parameter UV here taken from some domain D, which is a subset of R2 here. Okay. So R2 here is a real number. Okay, real number punya Cartesian plane. Okay. Right, so that's how you represent a surface using parametric equation here. So for example, so as an example, let me write it here. Example, the first one. So if you want to parameterize what? Let me try to parameterize a sphere here. Center 0, 0, 0. Yes, number x squared plus y squared plus z squared equal to 1. Okay. A sphere in the space here, x, y, and z. So you have center 0, 0, 0 with radius 1 here. Okay, radius 1. So if you have this one, so how we can parameterize this surface? So R here, the radius is always 1. So let me use what? Two parameter. How you can parameterize this one? You can use R, phi, and theta, for example. Phi and theta. R, phi, theta. Okay. So x equal to what? X equal to x phi theta is equal to, so let's make it, should be 1 sine phi cosine theta here. Y phi theta is equal to sine phi sine theta. Okay. So if you recall again from triple integral, if you want to convert from x, y, z punya coordinate to spherical, so you can use that way to parameterize this sphere. Z phi theta is equal to uh, cosine phi here. Okay, cosine phi. So that's how you can parameterize this sphere. Okay. So meaning that if you want to write it nicely, the equation, so let me write it below. You can represent as sine phi cosine theta I plus sine phi sine theta j plus cosine phi k here. Where phi here you can take from 0 until pi, 180 degree, and theta here from 0 to 2 pi. Okay, 2 pi. Wait, that's it. So that's how you parameterize sphere. And there are many other example. So, for example, if you want to, yeah, maybe another example to see this one. Second example, maybe you want to parameterize sphere. Not sphere, I mean cylinder. So x square plus y square equal to 4, for example. Okay, this is in the space. And then here z from 0 to 1, for example. Okay, so you have x, y, z punya dimension space here. So z from 0 to 1. So you have circle here, something like this. Okay, okay. So this circular, right, this here should be 2, right? This is 2. 2. Okay. So this will be 2 lah. This is 2. This is 2. This negative 2 here. Z is 1 here. The height of the cylinder is 1. So how to parameterize this one? You can parameterize as follow. Or you can use variable theta. Theta and Z here. Okay. So X here should be what? X here you can have as 2 cosine theta. Y as 2 sine theta. Okay. Because if you substitute here, this one here, you will get 4 here. Okay, you will get 4, right? You take x square, you get 4 cosine square. Y square, you get 4 sine square. Then therefore you have 4. You can factor out 4 and then cosine square theta plus sine square theta is equal to 1. So only one variable here for x and y. So you get this as what? 2 cosine theta I plus 2 sine theta j. And then plus, in the z direction, you can just use z, no? Z, k here. Okay, so you have two variables, theta and z here, theta and z. Where theta is taken from 0 to 2 pi and z from 0 to 1. Okay. So that's first way to represent a circle, a surface. So far, so good. Okay, good. Am I still with you? Lancar ke saya punya suara? My voice clear? Let
Yes,
me
Mr. No
check
problem.
that. Oh, okay. Baik. So next, let me talk on implicit. So make it brief here. So implicit form here. So you can represent as a label surface. Okay, if you recall again, multi-variable function, you have 3 variable function there, right? So if you have label surface, so this is represented a function there. Here you have f x, y, z equal to some constant. So this we call as a surface, right? Because a label surface for 3 variable function. So this another way you can represent it. For example, this way, these things, right? So this thing is f, x, y, z, right? So you let f, x, y, z equal to x squared plus y squared plus z squared. So this is a function of 3 variable, and then you take this level surface when this function equal to 1. So you get this sphere. Okay, so this one. So another way you can have level, representation of surfaces implicitly. Okay, baik. So sometimes because this is a closed surface, so you don't have any restriction there. So you take whole surface. Sometimes the implicit equation here is you can we write some over some region. let me make it D over some region D. D here is some region that will take this value X, Y, Z here. Right. This will be implicit form of what we call here surfaces. Then the last one is you represent it explicitly. So this is most common if you have a graph of two variable function. If you can represent Z, so this you can as two variable function over some. So you have Z equal to fxy there over some domain D here. Okay. So we call this a function of the variable, right? And then if you try to sketch it, the graph is some surface. Okay, this is some surface, and then simply restrict it over some domain D. So xy here taken from this domain over like xy here of this subset of real number again. Similar like what we did for parametric here. Okay. So example, so example for explicit form there. Yeah. For explicit form here, so let me look. Yeah, I think you may be familiar already with two variable function. So what? Simplest way one is maybe paraboloid. Okay, paraboloid. So example 2 here. Example. So you have z equal to x. Let me make it fxy equal to x squared plus y squared over. Let me restrict the surface. R here, let's make it as some circle x squared plus y squared less than or equal to 1, for example. Actually, this is greater or equal to 0, right? You add non-negative number, should be greater than 0 here. So this, you can represent a surface in this equation. Okay. We call it explicit representation. So you have what? A paraboloid there. Okay, this is height 1. Okay. Okay, then you will have the projection here. So this is your D lah, D. So this is what I mean by D. The value of XY there should be this one, right? This is circular shape, right? This D is there. Circular disc with radius 1 here. So if you try to sketch D here, so XY should be this manner, this shape. X squared plus Y squared equal to 1 is the boundary here, the circle here. 1, negative 1, negative 1, 1. Circle center 0, 0. And then our surface. So usually I did not write sigma here. So this one is our surface, the paraboloid there. Okay, this paraboloid. A part of paraboloid. Wait. So that's a little bit on the surfaces. So far, so good. That's it for the first part. So anything you want to ask? Any question? No question? So that means, do you have some comment there in the chat? No. So, yeah, yeah, sure, yeah. Jelas ke? I understand, understand? Okay, if no question, let me proceed then. So the main agenda, which is the surface integral. So now we talk on surface integral over scalar field. So let me define it. How we can define this surface integral over scalar field here. Okay. Wait. So this is the first part. Are you the same? Let me use A, B, C here. A, B, and C here. Okay. So what I'm talking just now about topic A. So now let us proceed second part, which is surface integral of scalar field. Integral of scalar. Okay. So as I mentioned before, you have this double sign integral, and then you want to integrate this scalar function ds, okay, over this what we call here surface sigma, and then this is somehow like a surface area. So I think you already what we call have strong background, right? If you recall, you have single integral there f dx there over interval ab. So this is just one-dimensional object AB here, right? So you can write it also as follow f dx there. And then you learn also before, maybe you should learn this double integral. You have double integral here. So now here a length here, right? This is a length. This is area here over some region here. And then what else? You learn also about triple integral df dv here. So you have three variable function. Now you have some solid, right? Solid in space. This is a volume here. So this is a volume. This is area. This is length. And perhaps you also learn also about line integral. So you want to integrate f ds there. C here. Okay. So this is an arc length, right? Similar like this one, length, because this is one-dimensional object. Only this one you have some curve, not only a straight line like this one, but interval here. You have more, somehow you can understand this generalization of this one. And then to extend, so here instead of a planar space, planar plane, right? This R here always on the XY plane, if you recall. And this one is any surface, okay, to object. So you can understand this is generalization of this double integral. Okay, double integral. Baik. So how to compute this thing? Okay. So if you recall, when you have this double integral, when you, what we call here, make the function equal to 1, then you have area, right? Area of R here. Similar concept here. So I think actually everywhere, if you make a function equal to 1 here, you get something like the quantity that you can measure. This is the length. If this equal to 1, you compute a length. If this equal to 1, you compute area. If this function equal to 1, you compute volume. Similarly here, if the function equal to 1, you compute the length of the curve C. So similar here. So if you let our scalar function here equal to 1, so you reduce the surface integral as follow. ds, right? So what is this? This is surface area of sigma. So you can understand as surface, just roughly speaking, you get surface area of sigma here. Baik. So now how we can compute this surface area? Okay, how we compute this surface area? How we can compute this surface area? Let me think about this. Oh yeah, you need to use back what I mentioned earlier about the parametric equation to represent surface, explicit one, and also implicit one. So let me give you some rough meaning using parametric equation of sigma here. Okay. So we know that you can parameterize surface. So we parameterize surface as follow. X u v I plus y u v j plus z u v k there. Okay. And then as I mentioned, UV over some domain there. Okay. Subset of R2. Okay. So for example, now if you have a surface in space here, X, Y, Z. Okay, you have some surface here. Okay, they have some surface here. This is our sigma. Okay. And then you see that you can go to the parametric world of variable u and v. So this one will correspond to, so this one, if I make it as a planar here, if I want to make it as a planar here, in the UV plane here. So I have UV plane there. UV plane. So let me make it bit here. Okay. And then this one. So let this, so this one will have some kind of this shape sample. Okay. Some kind of it. Okay. So this will be our D lah. So this will be our D here. Will be our D here. Okay. So recall again what you did when you compute double integral. You make a partition, right? To compute the double integral, you make a partition of this region, right? Similar here, you make a partition also. So let me just use another color here. Then you make a partition here with respect to U and then with respect to V also. Okay. And then I will have some rectangular shape here. So let's make it this box. Okay, this. Then this one I can correspond to here. And then it make some patch there, a patch of a part of surface there. So, okay, so maybe this one in the middle, maybe it will leave somewhere here. Okay. Somewhere here. Okay. So what we need to compute this? What we need to do in order to compute the area of this one? So one way is we use this parametric equation here. Okay. So let me use blue color here. So you see that you can understand this is U direction. Okay, so this is U direction here. And then this is V direction. I'm sorry, this is going to V here, right? Going increasing V. So this is increasing V. This is somehow increasing U here, more or less. So just roughly speaking here. Okay, and then from here, this point correspond to somewhere, some place here, this point. Okay, right. Now, if I go to this direction, so how I can compute the direction of this? So macam mana saya, how I need to compute actually, so this V, right? Going V here. So actually how I can compute this direction is, I need to, what we call here, differentiate this one with respect to V. So let me just use black color. So you have this, for example, R sub V here. Okay, this direction should be R sub V. Similar here, you have this line should be R sub U. Okay. So if you recall again, if you learn about the C here, okay, and then you can represent as RT here, right? Then if you differentiate here, R prime T, somehow this is the direction of the curve, right? You have direction of the curve, the tangent. This is tangent to the curve then. If you differentiate this for curve. For curve, if you differentiate, then you get this direction here. And then tangent to the curve, and then this is direction. Similar here, only here you have two variable. So for variable v, you have direction of v there, variable u, direction of u there. Okay. So now you have this direction, right? You have this direction. Next, what else I need? So I need to compute these things. Okay. I need to compute area, I'm sorry, area of this patch. Okay, patch of surface here. Okay. The red color here represented by this box. So recall again, and not recall again. From here, I know this some change in U here. I mean some you have small length in U here. And this one also you have small length in V here. So if I want to, yeah, oh, okay. So if I want to compute this thing, okay, if I want to compute the area here, so not enough only I need to know the direction. I need to also know the magnitude. So I will use this change as the magnitude for this vector. So for example, that I did not, for example, I will multiply this one, delta V here, and then this is delta U here. Okay. So how this will be a magnitude with this kind of scalar for the vector. Okay. All right. So now I have everything here. So what next is, actually, I want to compute the area here, right? I want to compute the area here. But here the information I have here, not really the area here, but you can compute some area of parallelogram here, right? If you have two vector, and then you can compute this area of parallelogram. So you can approximate the area of the red patch using the area of parallelogram here. Okay. So that's the partition that we need to use. So you will partition using these things and then correspond to the vector there with this scalar multiplication. And then you will use this as the approximate things to the area of this red patch of the surface. Okay. Wait. So now how to compute the area here? The area you can use the formula. Yeah, I think you know already. If you compute the magnitude of a vector there, area of parallelogram. Okay. V R sub V cross, let me get U first. U R sub U cross delta V R sub V. Excuse me. So that will be the area of the parallelogram. So, and then you see that this is a scalar. This is scalar, and then you can pull outside of the magnitude of a vector, right? Because this is a vector, it's a vector. So again, if you make a cross product, you get a vector. Then you can compute the magnitude of that vector. So this is similarly you have R sub U cross R sub V delta U delta V. Okay, this is quantity when you make a, if you remember, you make a Riemann sum for single integral, double integral. So this is what you have, Riemann sum. So this with variable I, J there, you take a Riemann sum, make a partition very small, and then you take a limit there, right? Make an area 0. So more or less come across to this formula. So these things, ds sigma. So you will have this formula, sigma. You have R sub U cross R sub V, R sub V, and then you have du dv. Okay, so that's how you will compute the surface area. Okay, this is the formula for surface area using parametric equation. Okay, so far so good. I give you a little bit idea on deriving actually this formula. So not the rigorous one, just roughly meaning of this formula. And then that's how you compute the area. Baik, so far so good. Okay, good. Any question? I'm sorry. Is it okay? Understandable?
Yes,
Yes,
sir.
Mr.
It's good enough for me, sir.
Okay, good now. Okay, I hope you are still with me. Okay. If I'm not with you, please interrupt me. Okay. Baik. Next, once you derive this formula, so let me look at example. So let me look at example. So I think I just choose simple one. So compute the surface area of these things. Let me use, yeah, this cylinder maybe, much more simpler. Because you can also compute directly, right? The height and also the circumference there. Let me just copy here. Where is it? This one. So given this our cylinder surface, so here you will have what? So I want to compute this surface area using that formula. So I need to do what? So if you recall again, I have this one given by r theta z, right? And then I have r sub theta cross r sub z there. D theta dz. Okay, d theta dz. So I need to compute these things. So what is r sub theta? What is r sub z? Okay. So r sub theta is you differentiate this one with respect to theta. Okay. So what you will get negative 2 sine theta I plus 2 cosine theta j. Then it's just 0, right? No variable theta here. Then you need to differentiate this one with respect to z. R sub z, we get what? This is 0. No variable z is 0 also. What left is just k here, right? Z. You differentiate, you get 1. Okay. So now just to compute this thing, so what is R sub theta cross R sub Z? So you compute first the cross product. So I think you know how to compute this one, right? So just to recall, so you have 0 here, 0, 0 here. So I, J, K here, right? So to compute the first component should be you just take care about this one, right? You will have 2 cosine theta. 2 cosine theta I. Layer minus, you will close this one multiply this one, and this one multiply this one. You get negative 2 sine theta. Negative 2 sine theta J. And then the last one, you will have this part, right? Okay, then you have this multiply this 0, this multiply this also 0. Yeah, 0 plus 0, okay. So this one just, you have 2 cosine theta I plus 2 sine theta J. Okay. And then you take the magnitude. So compute the magnitude R sub Z. So you get what? You take square of this one, right? So you 4 cosine square theta plus, and then the second component, you get 4 sine square theta. And then the third component is 0 plus 0 square. Then you take square root. Left is just 2. So now you already compute these things, and then we just substitute this inside the formula. So you get what? Yeah, so let me write it here. Is equal to 2 d theta dz. Okay. So if you see here, our domain of integration is theta is runs from 2 to pi, 0 to 2 pi, and z from 0 to 1. So if you draw it in theta z, this is 2 pi, this is 1, so it's just a rectangle. So this is easy shape, right? So you have limit 0 to 2 pi and 0 to 1 here. Because E integral is with respect to theta, we have 0 to 2 pi, and then outer integral here 0 to 1. So that's it. You try to compute here. So what do you get here? 2 pi times 4, you get 4 pi. 4 pi, right? So that's how you find the surface area using this surface integral. Okay. Okay. So far, so good. Okay, guys. So yeah, like something like lecture here. I do some calculation with you. I hope you can follow this calculation. Okay. So if you compare here also you can calculate directly, right? So you have what? What is the circumference here? Should be 2 pi r, right? R is 2. So 2 times 2 is 4 pi. So you get 4 pi. The circumference of the circle, height is 1. So you get 4 pi. So somehow you get the same answer there. Right. So yeah, that's an important part about this parametric form. So sometimes we are not using parametric as your curve, the representation for the surface. Sometimes we use implicit or explicit. And that formula, this formula, where is it? Yeah, this one can be derived also for what we call here explicit and implicit. Okay. So using this parametric punya derivation, so I use it back. So you see that if you have explicit, right? Explicit form of the surface there. Sigma is given by Z equal to fxy over some region R or D then. I used D earlier, right? It's also a special case, the parametric form of sigma here. So you can make it as R xy is equal to xi plus yj, and then z here is equal to this function, right? Plus fxy. Okay. Now xy is from D there. Okay, from D. So therefore we can derive the formula for this case. Okay. So if you try to derive, so you find the r sub x. So what I will get here? Get I 0, right? Plus f sub x. I'm sorry, this is k. And then you have r sub y. You will have what? You will have this is 0, j, because you differentiate here with respect to y, you get 1, plus f sub y k here. Okay, all right, sub y k. Okay, and then you can derive the formula, and then you will not, you find this one r sub x cross r sub y. You will get something like this, minus f sub x I minus f sub y j plus k then. Yeah, you will get this one. And then if you find the magnitude, it is just the square root there. F sub x square plus f sub y square plus 1. Okay, you get this thing. Okay. And then you just substitute the formula. So now our sigma ds is equal, our region of integration will be D here, right? D, because you have the domain of x, y here, D. And then, let me recall above. Yeah, these things should be what? This thing, square root of f sub x square plus f sub y square plus 1. Yeah, dx dy. So you reduce to the usual double integral. From surface integral, you get use what we call the usual double integral. Yeah. Okay. So that's it. So that's it. How you use explicit form. Similarly, if you have implicit form, you will get more or less similar form like this. So this is for explicit. So let me just write the implicit form. Have some like this one. Because you have big F just now, right? Capital F. You find the F here, okay? The gradient of F divide by the gradient of F. You dot with K here. This will be the magnitude of the gradient. This just the product, you make it positive, and then you have dx dy. Okay? So this if you are given implicitly. Implicit. Okay, implicit. Okay. Actually, if you try to expand this one, you will get this formula also. Okay. So far, okay. So that's the formula how to compute what we call here surface area. Okay. You have three formula: implicit, explicit, and clear is the parametric. Let me have something. Oh, yes. Okay, then let me rewrite again. The parametric one, you have R sub U plus R sub V dx. No, du dv. I'm sorry. Du dv is parametric. Okay, so that's a bit on what we call here surface area. Okay, can I continue? Is it okay? Or you want to take a break? It's almost 1 hour already. I think more than 1 hour. You want to take a break? 5 minutes maybe? Or you want just me to continue?
According to
Anyone?
you, Dr. Ali.
Yeah, just follow me, okay? Okay, if okay,
Okay.
let me continue. So I still have energy to write it here. Okay. Okay, so let me just continue then. So you have these three formula. So most frequently you will encounter this explicit form and also implicit form here. But anything, if you have implicit here, you need to reduce also to explicit form here. So this is a surface area, right? So there is no function, I mean function equal to 1. So if you have a function there, so if you have now a scalar ds, therefore you just, what? I'm sorry, I make it f here, right? So this is the same f. So let me write not f here. So I make it maybe what variable I don't use. Yeah, maybe sig p, maybe phi here. Okay, a scalar function here. Okay, it's just so for example, if for this one explicit form, so I will have this form e. So this here d here on xy plane, xy plane. Okay. And then you have sigma here, x, y, and z here you represent, you replace with fxy. Okay. Then you have the root there, f sub x square plus f sub y square plus 1 dy dx or dx dy. Okay, depend on when you choose later the order of integration. Okay. Or you have implicit form here. x, y. So although it's implicit form, then you use actually these things that to the explicit. So that's what I mentioned earlier. Although you have this formula, at the end you label UV. And then you have the magnitude R sub U cross R sub V du dv. Okay, so that's it. So let me write here dy dx lah. dy dx or dx dy. Okay, so a bit on the formula there. I think let me just show you one example how to use this one. So I think I take some example from the book before. This one. So let me try. I try to copy this one. Uh, I'm sorry. Okay, no. So let me try to do this example. So this I take from my book here. So compute this scalar integral surface integral. So the book here use interchange between sigma and s. For me, I have s here and sigma here. Okay. So we are going to integrate sigma x1 plus 2z ds here. Okay. So our scalar function is xyz is equal to x1 plus 2z. Okay. And then what is our sigma here? Our surface here is a portion of cylinder. This parabolic cylinder, yeah. Where it is, so let's try to sketch a cylinder first. Okay, let's try to sketch a cylinder. So what do we have? So you will have X, Y, and Z here. Okay, yeah, okay. So our other, you have this one, Z equal to Y square over 2, right? And then this is a cylinder, so you will stretch it along this, right? Along x-axis there, you will get something like this cylinder. Yeah, okay. But then only a portion of it, so you have triangular region. So what is you to sketch the region, and then meaning that you will cut along that to this cylinder, parabolic cylinder. I mean, so this is parabolic cylinder. Okay. So what do we have? So you have xy plane, xy, and then you have this is x plus y equal to 1. Should be this region, right? Because x plus y less than 1 should be in this direction. And then you have y greater than 0, x also greater or equal to 0. Meaning that you have this direction, this direction, this direction. So you have this shape. Okay, you have triangular shape, as it mentioned just here. So meaning that you need to sketch this one. Then the parabolic cylinder, we cut something like this one. Maybe I use the color. So our surface is just this thing. Something like this one. Okay. Okay. This is our surface. And then we want to integrate this function over this surface. Okay, over the surface. Baik. So, so what is the form of the surface? If you see from the, so if you see from here, you notice that it is given in explicit, right? Z equal to y square over 2. So you can have Z equal to f x y equal to y square over 2. So this is our sigma. given over the region this one. Let me make it R here. So this is over R. Okay. XY in this region R. So since it is in the what you call here explicit formula, then you can use the first formula I showed you earlier here, this one. Okay. So first find f sub x, what you get? You differentiate this one with respect to x. Get just 0, get 0. And then f sub y. So what dapat berapa? What do you get? F sub y here. You get y, right? Y. 2y over 2 is y. And then take square. F sub x square is equal to 0. F sub y square is equal to y square. Okay. Then you can find these things. Square root of f sub x square plus 1. So you will get 0 plus y square plus 1. Y square plus, okay, y square plus. Okay. Hope you can follow this one. Some calculation here. And next what? Next, you need to compute the scalar here. Okay, scalar. So scalar now, you will have x, y, z. Now z is substituted by this function. Y square over 2. So whenever you see z, you just substitute this function, this quantity. So what I will get here? What is the function? Yeah, x plus x1 plus 2 y square over 2, right? So I will just have x1 plus, you can cancel, you get y square. Is it y square? Yeah, y square. Yeah, y square. Okay, what next? Yeah, substitute everything inside lah, the formula. So the integral here, sigma x1 plus 2z ds is equal to, here is the region here, our R here, okay, our R. And then you have the function here, get x1 plus y square. And then you have also here 1 plus y square. Let's make it 1 plus y square also. dy dx. Okay. Can we integrate this one? Oh, yes, right. You can combine this power, right? 1 plus. So what do you get if you combine it? X, this is power 1. This is power half. You get 3 over 2, right? 1 plus y square power 3 over 2. Yeah, that's how you can try to integrate this one. dy dx. dy dx. Okay. Baik. So yeah, this one reduced to double integral. I hope you recall again, double integral, how to find the limit for these things, right? So this here, I don't choose this thing, right? If I choose this one, somehow I need to differentiate with respect to y first, so not easy for me. So let me choose dx dy instead. Dx dy. So I choose the order dx dy. Then recall again, then you need to find the limit, right? Limit of integration. So x plus y equal to 1. This should be 1, this should be 1. So now you need to draw a line parallel to x-axis, kan? This one, enter here and leave here. So x equal to 0. And then at left it y minus 1. 1 minus y. 1 minus y, right? 1 minus y. And then get 0 to 1 here. X equal to X equal to. Okay. Yeah, then this one, this one, I think I will leave it to you to compute the integral because this is just usual double integral. So you need to integrate first with respect to X and Y. Okay. So if easy, let me try to do it. So you have 0 to 1, and then you have X squared over 2, right? X squared over 2 here. And then you have 1 plus Y squared. Let me. So you have 1 plus Y squared, 3 over 2, and then you have X squared over 2. The limit is 0 to 1 minus Y, d1. Okay? Hmm. Yeah, not so easy. Not so easy. But this how you need to integrate lah. Do you have any idea to integrate this one? Okay. All right. Yeah, try to do it. So let me also search back from where I took this example. I think I take from some book here. Yeah, just Thomas calculus, I believe. I think it's from here. Surface integral. I hope they provide me the solution also, so that I can share with you. Example 4, I think, right? Example 4. Yeah, example 4. It should be there. Yes, you have this one. Yeah. Mm-hmm. Ah, should be square root here. Do I miss square root there? Yeah, should be square root, right? That's why I got complicated solution here. I'm sorry, I'm sorry. Oh, should be square root here, right? This one should be square root. Yeah, this one should be square root here. Yeah. Careless mistake. Okay, this one should be square root here. If you do it square root, then it will be easy to compute lah. Somewhere here. So this one you be have square root there. Okay, you have square root here. Okay. So you have square root also here. Yes, square root. Hmm. Then this will I think will be easy lah, because you have square root here. Then this one should be power 1. Right, this one should be power 1 because you have square root here and square root here. 1 over 2 plus 1 over 2 should be 1 then. And you have square root here. Now, yeah, I missed this one. Should be square root here. Okay. So that's it. So I think this one easy to continue. So you can try to, the answer should be not difficult to get. Okay. So if here I integrate first with respect to x, what do I get? So I will get 0 to 1, get x, let me write it here. 1 plus y square, you get x 3 over 2, right? 1 over 2 plus 1, you get 3 over 2. Limit from 0 to 1 minus 1. Yeah. Okay, so but this one is not easy to integrate. I think you need to integrate with respect to y first, so that you get easy form. yeah, you need to integrate with respect to y first. dy dx. Then this one should be this direction. You will have y equal to 0. And then here y equal to 1 minus x here, right? Because this is y equal to 1 minus x here. Yeah, this thing I think much more simpler compared to you integrate first with respect to x. Then from here you will get, yeah, you will also like 0 to 1 here, right? 0 to 1 here. You get 0 to 1 the same. And then here you integrate with respect to y, you get y plus y cubed over 3. Okay. Limit 0 to 1 minus x dx. Yeah, now this is simpler to compute. Because you substitute the value here, you expand everything, and then you multiply the power x here, and then you can solve it. So this one, so I will leave it to you to do the calculation. So if you refer back to the book there, the answer should be 284 over 945. 284, 975. 45. Okay, yeah, all right. Okay, so far so good. So already 248. Are you still listening to me? I'm not sure because maybe a little bit many things you need to listen. So far so good. Hope you get some idea then. Yeah, if you
Okay,
have any question, you
I
just
understand, Mister.
okay, okay. If you have any question, you just ask me. Okay, all right, okay, thank you. Okay, okay, okay. So if no question, maybe the last part. So actually, this is the last part should be surface integral over vector field. So it's okay. So let me just talk about scalar surface integral over vector field. As I mentioned, it is a flux integral. Okay, this is a flux integral here. So you see that the C, right? Surface integral of no, thank you. So now let me just move to the last part. So this integral over vector field here. So as mentioned, we compute vector field, the surface flux integral. So how to compute a flux? So if you see the formula there, the vector field you dot with n here, the orientation of the surface. Now orientation of the surface plays important role. ds over sigma here. Okay. So you need to choose which direction you want. Okay. So that's why we orientable surfaces. Example, this surface. So you want to compute the vector field using this direction or the other direction. So you need to choose the direction of the vector field and the surface. So similar thing, compute here. So you see here, this is what? Vector dot a vector, right? So it becomes a scalar. Vector dot vector or scalar product here. You become a scalar. That's why earlier we defined how to compute scalar function punya surface integral. And then we can use that formula to evaluate this flux integral. Okay. So another things you can understand this one. So why we have dot here, you can measure the angle, right? So if the dot equal to 0, what does it mean? It is orthogonal to each other, right? So you see that if f dot n equal to 0, meaning that what? What does it mean? If two vectors are 0, they are orthogonal to each other. This is N, this is F. Okay. So meaning that the F is just go through the surface. I mean, follow the surface, not going through there, more or less. Lah. So this is 90 degree F. Okay. So that's so for example, if F dot N is less than zero, less than zero. So meaning that the angle should be greater than 90 degree, right? This N dot F. So you have more angle here. Oops. You have more angle there. Okay, you have more angle. So meaning that instead of going the direction of N here, it go the other direction. Okay? You go to this direction. So if this is your N, your vector field going away, not the direction of N. Opposite direction, more or less. If it is positive, then you have acute angle, right? So you have something like this one. And then this is F. So you can understand it's the direction of the N. Huh? So you have this is your N, and this is your F there. Okay? So that's why we call it as a flux there. It's come from the physics there. If we call where the electron, so how they compute the flux, all of that is right. And yeah, we have to compute, right? You have to compute. So how to compute these things? Yeah, you use to. Yeah. So now we have more nice form because if you have a parametric form, yeah, you normal. Okay. Okay. So by these things, if you substitute into the formula there, so you will have F dot N ds. So this is unit normal of the surface, okay? Unit normal of the surface. You choose. And then you can just choose either positive or negative, right? If you are positive or negative then. Depends where you want to choose now. So you will have sigma here, F, I mean not sigma, you have D, right? D, F, this is R, U, V. You substitute the value of F, X, Y, and Z in terms of variable U and V. You dot with this one, you need to choose. This one you need to choose plus minus R, U cross R sub V. R sub U cross R sub V. So depend on the question lah. Question. So in what you want to choose. Sometimes you can choose one because the other is just negative of it. Then you have du dv. No, I'm sorry. ds, right? Not du dv, ds. So what is ds? What is ds here? ds here, if you recall again, is this thing. The three things. The three things that we have computed earlier. This is our s. This is ds. This is ds. This is ds. Therefore, in parametric form, ds is these things. Okay. So what is this? Not very good. Oh. So this one should be equal to ds here is just the magnitude of r u du d. We will cancel out this one, right? Because the scalar you can pull outside the dot product and then you cancel with this one. So the formula will look like this one. F R U V dot plus and formula for implicit form or explicit form. So let me show you for explicit form here. You have E there, you have F X Y, and then you have F X Y. And then if you try to what we call here multiply, so what do you get? What is n here? What is our n? Let's come here. What is n? Our n here is, if you recall again, z equal to fxy here, right? So you can make it as a label surface. F, x, y, and z here equal to z minus fxy equal to 0. Okay? So this is a label surface. And if you notice that if you have a label surface, if you take a gradient, always normal to the surface. So this one always orthogonal to the surface or normal 90 degree, I mean, to sigma. And then to make it unit, just make it f divided by the magnitude. Okay. Okay. So this is the, and then you can choose either two direction, plus or minus. Okay, plus or minus. So you have, this is our your n lah. So this is your n. Okay. So this will be what? The n is plus minus gradient of f and then magnitude of f there. Multiply by ds is f sub x square plus f sub y square plus 1 dy dx. Okay, dy dx. And then some simplification, you notice that what is this? What is the gradient here? Because we know this one, right? So what does it mean by gradient here? Let me write again here. So the gradient should be, f should be, you will differentiate, right? This function with respect to x. So f sub x I plus f sub y j plus f sub z k. Okay. Then this one, if you differentiate with respect to x, you get negative f sub x. This one negative f sub y. And then you get k plus k. Okay. Your gradient. And then the magnitude is what? The magnitude is just, you take square and then take square root. You get what? F sub x square plus f sub y square plus 1. Okay. And then you can substitute these two things inside this, and then you can simplify everything. Okay. Let me copy this one. And then kalau if you substitute this here, so what you get? This is these things, right? And then gradient of f is these things. So you can cancel this one with this one, scalar. You can pull out when you have a dot product there. So what left in the explicit form, you will notice you get this formula. F x y f x y, and then I will have plus minus negative f sub x I minus f sub y j plus k. Okay, and then yeah, that's it. You cancel this one with this one, and then you have dy dx or dx dy. So you need to remember this formula, and then you need to choose which one you want to negative or positive one. Okay, yeah. So this will be the formula. And then the last formula is if you want to have the explicit one. So actually the same like this one. So only this one is what? For implicit form. If you recall again, for implicit form is just something this one divided by So just let me write it here. So this is for explicit. For implicit, you will have something like this one. X, Y, F, X, Y. And then you have plus, minus, F, and then you have the magnitude. And the S there should be magnitude of F divided by, you make dot product with K there, if you recall. Okay? dy dx. Okay? And then here, if you try to simplify, you will get this formula. So this will equal to x, y, f, x, y plus minus this thing. Then you have f dot k then dy dx. Okay. That's right. Yeah. If we stop. So how? Do I give you the example or we can stop here? I'm not sure.
We can stop here. It's
What do you
okay,
think?
Doctor.
Yeah, is it okay if we stop here? Yeah, because too long already. I think around 2 hours.
Yeah,
Is
I think it's
it
uh
okay if we
covers all the material. Yeah, and the
yeah.
example is
I
enough.
think we can stop here. So this I just check you. Okay, good. So I
Okay,
think we can stop here. So let me stop sharing. Uh, So thank you very much for your attention. Yeah, for those here listen to me, I really appreciate it. Thank you very much. Yeah, I pass to you, Dr. Jovian. Yeah.
okay. Thank you very much, Dr. Ali, for a wonderful, insightful, and inspiring lecture today. We truly appreciate your time, effort, and the valuable knowledge that you have shared with us, yeah, with our student in the vector calculus class, yeah, through UGC, yeah, UNDIP Global Classroom Program. I believe today's session has not only depend on the students' understanding of the topic, but also broaden the perspective and how mathematics can be connected to various advanced theory and real-world application. We sincerely hope that all students gain meaningful insight from this lecture and can continue, yeah, tomorrow, yeah, for the Green's theorem, yeah. Okay, Dr. Ali, on behalf of the Department of Mathematics, Faculty of Science and Mathematics, Diponegoro University, I would like to express our deepest gratitude for your kind contribution and collaboration. Yeah, yeah, please accept or apologize. Yeah, apologize if there were any shortcomings or inconvenience during today's session. To all students, yeah, please give applause
Okay.
to Dr. Ali.
Yeah.
Ya, tolong beli aplausnya ya, aplausnya buat Dr. Ali ini.
Okay.
Ya, pakai riak nggak apa-apa.
Okay. Thank you very much. Yeah, no problem. Yeah.
Iya,
Okay. Okay. Thank
oke.
you guys. Thank you
eh,
very much. Yeah.
Thank you everyone ya for attending and participating today ya.
Okay.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Okay. Good afternoon again. See you again. Okay. Goodbye.
Waalaikumsalam warahmatullahi wabarakatuh.
So
Terima
I
kasih.
can
Thank
leave,
you,
right?
sir.
Yeah. Okay. Okay.